Alright, this video contains the solutions for exercise set A questions for chapter 10, questions about Taylor series. Number 1, we were supposed to find the first 4 non-zero terms and the general term of the Maclaurin series for the sine of x squared and give its interval of convergence. So we know that the series for the sine function is, well, you can look at that in your notes, and the series for sine of x squared, we just substitute that in for everywhere we see an x. So that series will be x squared minus x squared cubed over 3 factorial plus x squared to the 5th over 5 factorial. That's 3 terms, one more, minus x squared to the 7th over 7 factorial. And the general term would be, looks like we have x squared to the odd power. So that's x squared to the 2n, and if we were starting here with 0, that would be the 2n plus 1 power over 2n plus 1 factorial, and it's alternating times -1 to the, started with 0, so that'll work. Notice that this is just exactly the same thing as the general term for the sine function with an x squared plugged in here. Alright? And whether or not, if you were thinking about whether you have to simplify this or not, that would be x to the 6th, x to the 10th, x to the 14th, and so on. But on the AP test, and for these purposes, you can leave it unsimplified like that, and that's okay. Use the series in part A to find the first 4 non-zero terms and general term of the Maclaurin series for x times the sine squared of x squared. So we're multiplying the whole thing by x. That's just going to bump the power of everything up by 1. So now, since we're doing that, I'll simplify this. That's x to the 6th, so when you multiply by that, we'll have 1 more x, and 1 more x, and 1 more x. There's the first 4. The general term is going to be just like this, but we have 1 extra x. So all I'm going to do, I'm just going to leave it exactly like I had here and put 1 more x on there. Alright? Find the first 4 terms of the general term of the Maclaurin series for, this is number 2 now, unrelated to those. X squared over 2 minus x squared. Well, this looks like we want to match it up to the geometric series, 1 over 1 minus x squared, and this is the non-negotiable. That has to be a 1. So I'm going to rewrite that x squared over 2 minus x squared is equal to, I'm going to factor out the 1/2, and I'm going to make that 1/2 x squared on the top over 1 minus x squared over 2 on the bottom. Okay, if you take a second to look at that, see if you multiply that by 2 over 2, you get the same thing as that. I just basically factored the 1/2, factored the 2 out of the bottom and made it a 1/2 on the top. A little bit of algebra there for you. So now this is our first term. I'll write it as x squared over 2, and the multiplier is also x squared over 2. So the next term is plus x to the 4th over 2 squared plus x to the 6th over 2 cubed. Every time the multiplier is x squared over 2, so every time I'm adding a couple of x's into here and another 2. And the general term would be x to the even power over 2 to the just regular old counting number, right? So these are getting doubled, but these are just the 1, 2, 3, 4. Notice that each time that power on the top is twice as big, not alternating. So that's it. And, oh, wait. Looks like I missed interval of convergence here. I just noticed it in this problem, but that's very easy for this one. Since the sine function, since the series for the sine function converges everywhere, then if you change what the x is, it still converges everywhere. Now this one, this is a geometric series, so that's another story. The interval of convergence. For a geometric series to converge, the r must be between -1 and 1. So that means -1 and 1. The r, the multiplier, must be between -1 and 1. Now when I multiply through here, doing a little bit of algebra again, oops, 2 times 1 is 1. If I square root everything here, it looks like the x's that will work, x is going to be between, it's actually, of course, x squared can't be negative, but the negative values of x can still satisfy the less than 2 condition, so let you think about that for a minute. Make sure that you're okay with this. That's the interval of convergence. And with a geometric series, you know that if you try the endpoints, it's not going to work. The endpoints in a geometric series are going to give you the 1, 1, 1, 1 and the 1, minus 1, 1, minus 1. They're going to do that every single time. So you can go ahead and test them if you want, but they're not going to work. All right. Number 3. Use the Maclaurin series for e to the negative x squared to find this limit. All right, well, let's go ahead and find that first. I'll write that up here. E to the x, let's see, I'm just going to plug negative x squared in for all the x's. That'd be 1 minus x squared plus x to the 4th over 2 factorial minus x to the 6th over 3 factorial, and so on. Right? Just plugged in the negative x squared for wherever x shows up in the series for e to the x. So now, what does this look like? We got 1 minus x squared minus e to the negative x squared. So let's see, 1 minus x squared minus, and then now that I have the series for this, I'll substitute that in. 1 minus e to the squared plus x to the 4th for 2 factorial. And that's probably enough terms. If I need more, I can go back. And I want that over x to the 4th. Well, look, 1 minus 1, that cancels. Negative x squared plus x squared, that cancels. So that's equal to, I was lazy there, I didn't write down my limit as x approaches 0. Should have. And the limit as x approaches 0. The 1's cancel, the x squareds cancel, and then I get, there's a minus sign out here, so that's going to switch all the signs of these things inside. So I have minus x to the 4th over 2 factorial plus x to the 6th over 3 factorial, etc., over x to the 4th. And having the x to the 4th here, that knocks everything down by 4 exponents. So that's the limit. X approaches 0 of a negative 1/2. 2 factorial is just 2, right? Plus x squared over 3 factorial, etc. And notice that the limit as x approaches 0, there's going to be x's in all the terms from here on out, right? This is the only term that doesn't have an x in it. So the limit as x approaches 0, of that is just -1/2. Right? All the other terms go to 0 because you just plug in 0. Right. So here's a case where you were asked to do a limit and it did not involve L'Hopital's rule. It involved sequences in series, or in particular a Taylor series. All right, here's another one. Number 4. Find the first 4 non-zero terms of the series for f. Don't be freaked out by the fact that this is piecewise. The only reason why they had to make it piecewise is because this is not defined at 0. There's a 0 over 0, or just 0 on the bottom even, situation. So we're going to go ahead and just look at the sine function and divide every term by x, right? The series for the sine function, we know what that looks like. Divide every term by x. So that looks like the first term of the sine function is x, divided by x is 1. The next term is x cubed over 3 factorial, so when I divide by x, so every single one of those odd exponents is going to get knocked down by 1, right? So now the general term looks like x to an even power over the odd factorial, right? Even power plus 1 odd factorial. And then my sign flip-flopper, if I start at, I have x to the, it looks like 0 at the start, so I must be starting at 0. And then that means -1 to the 0 will give me the positive first term. All right. Now, here's an interesting question. I want us to use part A to determine the nth derivative at 0 of this. Well, I think we better try some derivatives and see what happens. So, let's see. The first derivative of this is, let's see, the derivative of 1. Well, remember, we're not taking the derivative of this, we're taking the derivative of the series. So the first derivative of this would be the derivative of 1 is 0, negative 2x over, and 3 factorial 6. Right? Now, when I plug 0 in to that, I get f prime of 0 is 0. The second derivative would be, oh, I guess I have to go further than that, don't I? Sorry, I should have taken more terms. Let's see, where shall we squeeze them in? That's still going to be true, but I only took the derivative of that first term. When I multiply here, 4 times that, that gives me plus x3, 4x cubed over 5 factorial minus 6x to the 5th over 7 factorial, etc. The second derivative is going to be negative 1/3 plus 12x squared over 5 factorial minus 30x to the 4th over 7 factorial, and so on. That's going to be negative 1/3. And what do they want? They want use part A to determine the nth derivative at 0. Well, let's answer C first, because we have that right here. When you plug 0 into the first derivative, since all the terms have x's in them, you get 0, right? When you plug 0 into the second derivative, you get all these terms turn out to be 0, but you get a negative 1/3 here. So that means the derivative is 0. It has a slope of 0, but the concavity, the second derivative, is negative. It's concave down. So we've got a critical point, 0 derivative, negative concavity, so that means we have a maximum, right? So the indication why f has a maximum, that's because the first derivative is 0 and the second derivative is, oops, nope, I had it right the first time, didn't I? It's negative, less than 0, right? So you get a critical point, negative concavity. All right, now let's go back to part B and see if we can figure out what the nth derivative is. Well, it looks like the first derivative at 0 is 0. The second derivative at 0 is negative 1/3. How about the third derivative? Third derivative, that's the derivative of this. That's gone, right? That's just a constant. That would be 24x over 5 factorial minus 120x cubed over 7 factorial, etc. And that's equal to 0 because they all have x's in them when you plug in 0. The fourth derivative is equal to 24. Notice 24 is actually 4 factorial, right? It's good to know your first few factorials over 5 factorial minus 120 times 3. That's 360x squared over 7 factorial, dot, dot, dot. And so when I plug 0 into this, I'm just going to get this term. 4 factorial over 5 factorial is 1/5. Right? So it looks like the pattern is going to be the 0th derivative when you plug in 0, I guess would be 1 if you want. And the second derivative is negative 1/3. The fourth derivative is going to be positive 1/5. The sixth derivative is going to be negative 1/7, right? It's getting 1 over odd number. The next one, this is going to turn out to be 6 factorial over 7 factorial, and so on. So I guess that's what they're looking for in B, although I don't remember ever seeing an AP question like that. These are AP type questions. So I guess we could say for part B that the nth derivative at 0 is equal to 0 if n is even, right? And the nth derivative at 0 is equal to, let's see, the fourth derivative was 1/5, so I guess it would be 1 over n plus 1. And they seem to alternate, like the second derivative was negative and the fourth one was positive. So we're alternating like it was 2n to the, let me think about that for a second. Second one, so this is a little tricky. This is negative 1 to the, we want the second one to be negative and the fourth one to be positive. So I think we have to raise it to the n over 2 power, right? Only talking about the even ones. Oh, this is odd, isn't it? Sorry. My goodness. Sloppy. The odd ones are the zeros. That's odd. And then if it's even, we want 1 over n plus 1 is negative 1 to the n over 2. That would give me 1 here. That would be the right. So I could put plus 1 if that was the wrong way, but that's actually going to give me the right sign. So there you go. That's a little crazy, that question, that part B. But that's what's happening with those derivatives. All right, let's get number 5 in here, and then we'll do a new video for the rest. Use the fact that cosine x is equal to sine of x over 2 minus x to find the first 4 non-zero terms and the general term of the Taylor series for cosine of x at a equals x over 2. Well, little trig identity business here. The sine function is an odd function, and an odd function is a function that means if you have f of negative x, that's equal to negative f of x. It's one way of defining the oddness of a function. It has this property, and that allows us to say that here sine of pi over 2 minus x is equal to negative sine of x minus pi over 2. There's a little trick to this one. So cosine x is the same as this, which is the same as this, right? Now, first 4 non-zero terms now. Well, the sine function I know is, let's see, it's x, which in this case is this, and then that to the third over 3 factorial, and then that to the fourth. I'm just going to do 3 terms. I know they asked for 4, but just for space. Now usually it would be plus, minus, plus, but since there's a minus sign in front, that's going to switch everything. So it's going to be minus, plus, minus, and so on. And then the nth term is just going to be x minus pi over 2 to the odd power, right? Starting with 0 over 2n plus 1 factorial, and then the sign flipper-flopper is going to, let's see, is it going to be, if I start here with 0, that would give me a positive first term, and I want a negative first term. So there's your general term. Okay? That's the first 5. Next video will contain 6 through 10.